Welcome. In the previous video, we saw that an electric current, charge, and motion can produce a magnetic field. In this video, we'll see that a changing magnetic field can produce an electric current. Let's begin by observing an unusual phenomenon. We have two metal rings. They're both conducting rings. The upper one is next to the north pole of a bar magnet. Now, what I'm going to illustrate is with a red arrow, the current flowing through the ring. Now, right now, the rings are stationary, the magnet is stationary. There's no current flowing. When this magnet drops from the upper ring to the lower ring, you'll see a red arrow appear on each ring. Red arrow indicated an induced current in each ring. Let me repeat it. This time, look at the upper ring only. You'll notice as the magnet drops, the current flows up the front side of the ring, the near side of the ring. See, red arrow points up. Now let me repeat it. Focus on the lower ring. You'll notice as the magnet approaches the lower ring, the current indicated by the red arrow will come down the near side. There's the red arrow. So what's going on? Red arrow indicates that as the magnet leaves one ring, a current flows one way, just a momentary current. And as the magnet moves in front of the other ring, there's a current going the other way, a momentary current. Two key points. This is an experimental phenomenon. Changing magnetic field will induce electric current. Saw it in those rings. But the induced current is only present while the field is changing. That's why it's a transitory current. It appears while the magnet leaves one ring. It appears while the magnet approaches the other ring. Once the magnet stops, there's no current. This phenomenon is called electromagnetic induction. It is inducing an electric current in a coil. Of course, we used a ring, one-turn coil. Inducing an electric current in a coil by a changing magnetic field is called electromagnetic induction. The creation of an electric current through a magnetic field. Now, maybe you have done this experiment before. I think you probably have. Here's a very common situation. Credit card. Brown stripe has your account information encoded magnetically into that strip. You slide the card in, you slide it out quickly. And as you slide it out quickly, that magnetic information encoded on the brown strip moves in front of a pickup coil. It induces the current in the coil. And the pattern of those magnets, as you slide it out, affects the current that's created in the coil, and it's able to decode that digital information into your account information. That's a very common example of practicing this phenomenon, electromagnetic induction. How do we quantify the changing magnetic field? Use that to determine the induced current in the coil. Well, we start with a quantity called magnetic flux. Think of magnetic flux as the number of the field lines that pass through an area. The previous illustration had the bar magnet, field lines coming on the North Pole. Think of the flux as the number of those lines that pass through the surface of the coil. Now, the symbol for magnetic flux is the Greek character phi. In the equation, that's phi subscript b, b for magnetic field. Phi is the Greek letter for F, corresponding to F. So flux F, we use the Greek letter phi. So if you wanted to know how many magnetic field lines pass through a surface, say, well, it's going to depend upon how strong the magnetic field is. The stronger the field, B, the more field lines. Also would depend upon the size of the area. So you see the equation. The flux phi subscript B equals B times A. Then there's a cosine theta. How does a cosine theta enter into it? In the illustration, there's an area, A, and then there are 3 magnetic field lines coming in, field B. Well, it looks like those 3 lines all pass through the area. But we need to remember we can always decompose a vector into 2 perpendicular components. So in physics, we quantify the angle between a vector and a surface as the angle between the vector and the surface normal. The surface normal is a vector perpendicular to the surface. So there's the area A. Normal is illustrated by that dashed line. So we define the angle theta as the angle for the field encountering the surface as the angle between the magnetic field line B and that dashed line, which is perpendicular to the surface. Not the angle between the field and the plane, the angle between the field and the normal. So we see trigonometrically the side opposite the angle will be B sine theta. The vector is B, so that the side opposite the angle is B sine theta. That component runs parallel to the surface. It will never cross the surface. But the component that's adjacent to the normal, B cosine theta, that component will go entirely through the surface. So although it looks like, oh, the whole vector passes through, no, if we decompose it into 2 components, we see only the portion of the magnetic field vector, which is, careful the language, the portion that is either perpendicular to the surface or the portion that is parallel to the normal. B cosine theta is the component parallel to the normal. That's the part of the magnetic field vector, the field line that passes through the surface. So the flux phi sub B is equal to B, strength of the field, times A, the size of the area, times cosine theta, the portion of the field that actually passes through the surface. That's the flux. Unit of flux, Tesla meter squared. Tesla for the field, meter squared for the area. Of course, cosine theta has no unit. Now we come to Faraday's law. Michael Faraday, the chemist and physicist who discovered this phenomenon of electromagnetic induction, determined the law that describes the relationship between the changing magnetic flux of the coil, the induced EMF. We want to find the induced current, but we start with the induced EMF. The EMF, think of that as a source voltage. It's what drives the current. EMF, term that's used historically to represent what we can consider a source voltage. So how do we get the current? Well, simply Ohm's law. If you know the EMF that's induced in that ring or in that coil, the current will simply depend upon the resistance of the coil. So this is the formula for the induced EMF. We use our symbol epsilon. We used that before for a source voltage. The induced EMF, epsilon, comes from changing magnetic flux. And there's the formula. It's equal to minus N. N is the number of turns in the coil. We're considering the induced current in a coil, or in this case, the induced EMF. Once we have the EMF, you need to know the current. It's Ohm's law. It's going to be EMF divided by the resistance. Induced EMF equals minus N, number of turns of the coil, delta phi sub B, the change in flux. Delta is the change divided by delta t, the interval of time. In other words, it's the ratio of the flux change to the interval in time over which that change takes place. The change in flux may be large or small, but if that increment in time is very small, you can obtain a large EMF. In other words, you can either, with a large EMF, try to manufacture a large change in flux, or try to do something very rapidly, make delta t very small. It has to be a changing flux, delta phi sub B over delta t. Faraday's law. So here's the formula for the magnetic flux, VA cosine theta. How do we change it? Well, there are three terms. We could change B. We did that in that earlier illustration where I said, well, here's a ring, and we can move the magnet away from it or move the magnet in front of it. So the field is changing near the coil. We could change the area. You could take a coil and imagine you kind of flatten it and expand it. Or you could change the angle, theta, between the field and that surface. It turns out we are really good, we meaning, people in general, at making things rotate. It's much easier, or it's very easy to make things rotate than to execute many other motions. You could have a propeller or wind turbine blowing in the wind. You could have a water turbine being turned by flowing water. You could have a steam turbine being turned by expansion of water into steam. A lot of ways to make something rotate. We'll see later that becomes the basis of generating electricity. Now, in Faraday's law, you might recall there was a negative sign. Epsilon equals minus N, change in magnetic flux with time. What is the meaning of that negative sign? That is encapsulated by Lenz's law. The current induced in the coil, remember from previous video, a current flowing through a coil will create a magnetic field. Lenz's law says the current that's induced will form a magnetic field which opposes the magnetic flux change. Words here are very important. The current does not form magnetic field to oppose the magnetic field. It does not form a magnetic field to oppose the magnetic flux. It forms a magnetic field which opposes the change in the flux through the coil. Let's return to the earlier illustration I had of two rings. in a magnet. We'll start with the ring that is sitting next to the North Pole of a bar magnet. So the ring is to the left of that magnet. We envision the field lines coming out of the North Pole of the bar magnet and pass through the ring. Therefore, the coil has magnetic flux, those field lines, going from right to left through the coil. Field lines go from right to left. If I remove that magnet, what will the induced current do? The induced current will try to replace the magnetic field lines that have disappeared. Now, there's a right hand illustrated there, a photo there on the left. It shows you the field lines currently point to the left. If I remove them, the induced current will create field line going to the left. There are the fingers of the right hand curling up. So let's see it. We move the magnet down, induced current up creates the field to the left. Of course, it's transitory. Once the magnet is gone, there's no longer a change. The effect disappears. Let's watch again. We start with a magnet. We remove it by having the current flow up the front side. We induce magnetic flux to the left. One more time. Just point out, I'm illustrating the current flowing up this near side of the ring. Of course, current flows all the way through the ring. It's a continuous current flowing through the ring. So you imagine the right hand, the current flows through the ring, creates the field to the left to replace what has disappeared. And transitory effect. Now let's consider the other ring. And there was the one ring where the magnet moved away from. The other ring, magnet is going to move next to. At this point, there is no magnetic flux through the ring. In other words, there are no magnetic field lines passing through that ring. When the bar magnet moves in front of it, there are going to be field lines going from right to left. This induced current will always oppose the change. The first case, it wanted to replace the thing that was taken away. Now it's going to oppose the thing that's added. Since you're adding something that points right to left, it's going to oppose it with a current going the opposite direction as the other ring. See this current? See, there's a right hand to the left. It shows you if the current flows down the front side and, of course, up the other side, it will create a magnetic field pointing to the right. So let's see. There it is. It's a transient effect. Current flows down the front side, right hand. It creates a field that points to the right, opposing the new field from the bar magnet pointing to the left. Let's see it one more time. Right now there's no current, as that we bring the bar magnet, it creates an opposing magnetic field arrow. Of course, now the magnet is stopped. There's no changing flux, and the current goes away. So that illustrates you have the induced current, but the Lenz's law, how do I know the direction of the current? It's going to be in such a direction that the field created opposes the change in flux. Now we're ready to observe the basis of the AC generator, the alternating current generator. We're going to rotate something because it's very easy to make things rotate, to make them rotate continuously, to make them rotate at constant speed. we have two magnets, left and right. And you see the north pole of one magnet, field lines come out, go to the south pole, the other. So we have field lines going from left to right. We're going to put a coil in there. And as the coil rotates, imagine that at some point the coil is going to be lined up so the field lines pass through it. And as it rotates, field lines kind of pass on either side of it. Let's just try. As this thing rotates, it's rotating continuously between those magnets. And so the field lines that pass through it will change depending upon the angle between that ring and the magnetic field. Of course, I want to be careful. Remember, it's not the angle between the plane, it's the angle between normal to the plane that we're going to use. Okay. You can look at that and say, okay, I get the idea. As that ring rotates, there's going to be a changing flux to the ring. There's going to be an induced EMF. There's going to be an induced current. How do I get the electricity out of that? Well, it can be done. It's a little tricky. I'll show you a better way. Well, first, we'll consider what's happening here. The flux of the coil, phi sub b equals BA cosine theta. If you rotate this thing continuously, B is constant, A is constant, but the angle theta will change continuously. For uniform rotation, we said that theta is equal to omega t, where omega is the angular velocity, t is just the time. So as we had uniform rotation, meaning it's not speeding up, it's not slowing down, it's a constant angular velocity, omega. So as a function of time, the angle just changes continuously. Now we're going to derive something called the generator equation. That's Faraday's law. The induced EMF, epsilon, equals minus n, change in magnetic flux, divided by change in time interval. The name of this course is Prime Directive Physics. Operating under the prime directive, we do not use calculus. I'm going to give in for a moment and do a little bit of calculus. I'm going to put this in red. For those of you studying algebra-based physics, you're not responsible for what is in red here. You can ignore it, you can close your eyes. But for those of you who want to see how we use a little bit of calculus to derive this equation, I've decided to include it. Okay. Again, algebra-based physics, you can ignore everything on this slide that is in red. But here we go. If you want to indulge in a little calculus, you replace that delta phi sub b over delta t with a derivative. EMF equals minus n d phi sub b over dt. That's the derivative. It's an infinitesimal. So now we need to do the derivative. Here's the equation where we have replaced the flux, which is BA cosine theta. Remember, theta for uniform constant rotation is equal to omega. Theta equals omega t. So the time-dependent flux, we just placed into the equation, BA cosine of omega t. Now, remember, the magnetic field B does not change. Area of the coil does not change. Those come out. We have minus NBA, the derivative, d cosine omega t dt. We have to evaluate that derivative. Here it is. The derivative of cosine is minus sine. But we're taking the derivative with respect to t, whereas the argument is omega t. If you use something called the chain rule, again, a little bit of calculus, you find that omega comes out in front of the sign. Therefore, the derivative is minus omega sine omega t. Now you look at the equation directly above it. You can replace that derivative, the cosine omega t dt, with the value minus omega sine omega t. Notice the omega is going to disappear. The result is epsilon, the induced EMF, is NBA omega sine omega t. Now I'm back to the black text. Now you're responsible for this, whether you're taking algebra-based physics or not. This equation is one you should know, the generator equation. We finished the calculus, ignore the red. We started with Faraday's law on the upper line. Epsilon equals minus n delta phi b over delta t. That equation, well, it's fundamentally correct, but we really need to derive it for a particular application to make it useful. And what we've done is we have taken the particular application. The field is constant, area of the coil is constant, rotation of the coil is at a constant angular velocity omega, and shown that it gives us this equation right here. NBA omega sine omega t. That is a very useful equation. We're going to show you how that appears, show you how you can use it to solve a problem. But first, I want to show you a simpler and better design for an AC generator. The previous illustration, I said if you rotate that coil, you can find a way to get the electricity out of it. But a better way to do it is put two coils, rotate the magnet in between them. So as the magnet rotates, you see the coil on the left, part of the time the flux points left, part of the time it points right. Same thing, the coil on the right, part of the time flux goes one way, the other way. The coils are stationary. So now you can imagine, oh, I can make a coil of wire and I can attach that to an output. The output from that would look like the graph directly below. The generator, it's sine omega t. So the EMF looks like a sine function. So the function of time, left to right, you have a sine wave. That's what it looks like. That's the source of alternating current. It's an alternating EMF, but it, depending on the resistance, generates the current. Alternating EMF, alternating potential leads to alternating current. And this is the best way to do it. In fact, you don't need to stop at two coils. You could have instead of one pair, put three pair and get three phases of EMF coming out. Or you can have large generators with many phases coming out. You find some mechanical means to rotate the magnet, whether it's wind power in a wind turbine or water power, say at a Niagara Falls or at a dam where water's coming through, rushing over turbines, or steam power, whether you're burning coal or using nuclear fuel to generate steam by heating water, blowing that steam over a turbine, making it rotate, generating alternating current. Because we're so good at making things rotate, because this is such a elegant method here, rotating a magnet between pairs of coils, this is, of course, the dominant way to make electricity, and it's why we have electricity that is abundant and relatively cheap. Okay, let's look at a problem. Generator problem. Student made a simple generator I'm not suggesting you try this. I'm just made it up as a problem. By winding a pair of coils with 24 total turns, opening of each coil 7 centimeters square, and then rotated a 0.15 Tesla magnet between them at 1200 RPM. What is the RMS voltage output of this generator? Again, this is not something you want to go to your garage or shop and try to do. This is to illustrate how we work through this problem. Many things here we have to treat in the problem, and so we'll step through it. Here we go. Here's the equation we start with. NBA omega sine omega t. We've actually seen this equation in a previous lecture, but we wrote it differently. We wrote it like this. So for an alternating current source, alternating potential, we have some maximum voltage, V max, times sine 2 pi ft. Now you see, omega corresponds to the 2 pi f, where f is the frequency and rotation, the revolutions per second. Omega is radians per second. What about the NBA omega in front of the sine? That is what we called Vmax previously in a previous lecture, talking about AC current and voltage and so forth. So let's work through this now. The frequency of rotation is 1200 RPM. But in our equation, we have omega. So the 1200 RPM stands for 1200 revolutions per minute, RPM revolutions per minute. If we do dimensions, we need to convert this to seconds. Either think of it as revolutions per second, rotations per second, cycles per second. We get rid of minute by saying we multiply that by 1 minute over 60 seconds, 20 hertz. Hertz is the abbreviation, the symbol, unit for whether you say rotations per second, revolutions per second, or cycles per second. We went from 1200 revolutions per 60 seconds to 20 hertz, 20 cycles per second. Omega, which is radians per second, is equal to 2 pi f, because each rotation or revolution or cycle is 2 pi radians. So you multiply that cycles per second by 2 pi. You have 2 pi radians per cycle. And you plug in the number 2 pi times 20, 126 radians per second for the angular velocity. Here is one that a lot of people will make a mistake. Area of the coil, 7 centimeters squared. Mistake would be, just look at the C for centi and enter only 10 to the minus 2. But when you see cm squared, centimeters squared, you have to remember that not only is the meter squared, the centi is squared. So it doesn't look that way, but the cm is 1 unit. The whole thing is squared. So you put 10 to the minus 2 meters squared. So it's actually 7 times 10 to the minus 4 meters squared. Make sure you understand that it is, I know from giving many exams, extremely common mistake. See the C and put 10 to the minus 2. Remember, centimeter, 1 unit, you square the whole thing. Now we solve for Vmax. This is the top of that sine curve. So it's NBA omega. And we go back to the problem. 24 total turns. Okay. B. Go back to the problem. 0.15 Tesla magnet. We'll put that in. We now have A. 7 times 10 to the minus 4 meters squared. We have omega, 126 per second. What happened to the radian? Radian is a little bit of a non-unit. You can have radian alone, you can have radian per second, but anytime you have an equation, when you see meter, radian will disappear. We have a meter squared, we have a 10. So the radian disappears, we're only left with per second or second inverse. Multiply that out, you get a number which is going to be Tesla meter squared per second. Again, you don't know what that conversion might be, but the context, you're calculating a maximum voltage, unit must be volts, 0.317 volts. That is the top of the sine curve. You have that oscillating up rapidly 20 times a second. It's going through the cycle. The top of the curve is Vmax. The bottom of that sine is minus Vmax. But remember, you need to go back and review a previous video. It is extremely convenient to use quantities that we can treat as constants. And for AC circuit, we like to use RMS quantities. You measure with a meter, you get a number. You don't get something that's wildly oscillating, you get a number. You treat it as a constant. So what is the RMS voltage? Go back and read the problem. The problem says, what is the RMS voltage? Not what is the maximum, what is the RMS? And if you need to go back and watch the previous video, RMS 0.707 Vmax, which gives you 0.224 volts. The RMS voltage comes out of that generator. So to study this problem, it takes you through many of the details of how to use that equation. That's the introduction to generating electricity from a changing magnetic field. Thank you for watching this video.